All right, so this is heat and calorimetry. We're pretty much going to cover everything for this chapter in this lecture, and then the rest of the week we'll look at problems. All right, so the first thing to realize is how things heat up, and this is pretty much true for all substances, but not all. The most common substance you're going to come across in this chapter is water. So in this diagram here, we have a Bunsen burner heating up a substance in the beaker. So let's say that this substance in the beaker is ice at negative 30 degrees Celsius. So we're starting in the solid phase. So on the diagram here, we're starting down here in the lower left corner. That's why I picked negative 30. The ice is starting at negative 30. Now water has two important temperatures. The two important temperatures are 0 and 100. This diagram didn't label 100, but if you look here, 100 would be like right there. Okay, so 0 is the melting point, 100 is the boiling point, and this is what pretty much all substances would do if you started adding heat to it. So notice the x-axis is energy added. Okay, so like we got this Bunsen burner here, energy in the form of heat. Heat is a form of energy. Heat is being added to this sample of ice. Okay, and then we plot out what happens to temperature. So this y-axis here is measured in its temperature in degrees Celsius. Okay, so clean this up. You know what? Let's make this bigger. So we're looking at what happens to the temperature of a substance as heat is added. So we're going to make this nice and big. All right, so heat is being added. So is the ice that we're starting with, as when we start to add heat to it, does it instantly go to liquid? In fact, it goes through two steps. The first thing that happens to the ice is the temperature rises until we get to 0 degrees Celsius. Now, at 0 degrees Celsius, the ice begins to change phase. It's not going to happen instantly. There's this period where we have ice and water together. Okay? The thing to realize here, and there are probably several of you that have never had this realization because it's kind of counterintuitive. What most people think is when you add heat to an object, the temperature rises. Is that always true? No, because during a phase change, the temperature stays constant. So notice we're still adding heat. This entire time, we're adding heat to the substance. Okay, but during a phase change, the temperature levels off. Okay, now when is the temperature going to rise again? Right here, the temperature starts to rise. That's the point where the last speck of ice has converted to liquid water. So once the last speck of ice is gone, the temperature continues to rise until we get up here to 100 degrees Celsius. And then what happens at 100? It starts to convert to steam. So we have another phase change. Temperature levels off, even though we're adding heat. So it converts to steam. At this point right there, the last speck of water has been converted to steam, and then the temperature rises again. All right? Now, if you're ever asked the question, if anybody ever gives you the choice, do you want boiling hot water dumped on you, or do you want to stand in front of like an open steam valve at like one of the Torrance refineries? Which one would you choose, boiling hot water or steam? I would take boiling hot water, because boiling hot water, you know you're dealing with 100 degrees Celsius, right? Steam, I mean, I don't know how hot it gets, but we'll just call it really, really hot. I'm sure there's an upper limit before like the water molecules break apart. Okay? So that's the trend of what happens when you heat up substances. Now, let's look at the equations. Now, when you heat up a substance, we have two types of heat. Notice I put types in quotations. I mean, because heat is heat. It's a form of energy. But you'll see what I mean here. We got two types of heat. So the first type is specific heat. So specific heat is when you're working here, here, or here. Now what do those three regions have in common? Temperature is changing. When heat goes into the substance, the temperature changes. Okay, that type of heat, we refer to it as specific heat. And the specific heat equation is Q equals MC delta T. That's a very important equation. Now, what is Q? Heat energy measured in joules. M is mass measured in kilograms. C is the specific heat, which I'm going to talk about in a second. I want to explain this unit. It's in units of joules per kilogram degree Celsius. And then delta T is change of temperature, which could be degrees Celsius or Kelvin. It doesn't matter because you're talking about temperature change. In yesterday's lecture, when we did gas laws, if you're doing a gas law problem, you have to be in Kelvin. There's no choice. But why here does it not matter? Because we're talking about change. We're talking about change of temperature. You know, if the temperature in this room went up by 5 degrees Celsius, the change in Kelvin would be 5 Kelvin. Because Celsius and Kelvin are always separated by 273. So change is the same when you're talking about, or you could be in Celsius or Kelvin when you're talking about change. All right, now, specific heat, the unit. So water, again, it's the most common substance. Water has a specific heat of 4,186 joule per kilogram degree Celsius. And you don't need to memorize that. I'm going to give you specific heats. On the quiz, on the test, specific heats are given. Don't memorize them. Okay, but what does this mean? So say, for example, so I'm holding a water bottle in my hand. So if you're watching the video, so say, here's my little, I can't draw, but so here's this box right here represents 1 kilogram of water. If you took 1 kilogram of water and changed the temperature by 1 degree Celsius, so that could be 30 to 31, it could be 52 to 53, any change of temperature of 1 degree Celsius, how much energy would be required to do that? 4,186. So the specific heat, it's telling us how much energy is required per kilogram per degree Celsius. Does that make sense? Now, another substance, just so you can see how this works, another very common substance is copper. Now, what would you expect? Should copper have a higher specific heat or a lower specific heat? Lower. Okay. In general, a low specific heat means that it heats up easier. Would everybody agree that copper heats up easier than water? Copper heats up real nice. In fact, you go to Williams-Sonoma down the street up here, down the street, what's the real nice cookware made of? Copper. Why do people like copper cookware? Because it heats up real easy, heats up real nice, but it's very expensive. Copper has a specific heat of 387 joule per kilogram degree Celsius. So meaning, you know, if you had 1 kilogram of copper, you change the temperature by 1 degree Celsius, it takes only 387. So the lower the specific heat, the quicker or the easier the substance heats up. Okay? Okay, so now let's talk about the other type of heat. Latent heat. So latent heat is when you're working here or here. Phase change. It's the heat involved with a phase change. Now, the word latent is a great SAT word. Anybody know what the word latent means? No. Hidden. I like the word hidden. Hidden. Latent means hidden. Now, why would we refer to this type of heat as being hidden? It's kind of an obvious question. Because what do you expect to happen when you add heat to something? You expect the temperature to change. But is that true during a phase change? No. Nope. During a phase change, temperature stays constant, so we call it hidden or latent heat. Now, the equation for latent heat is Q equals mL. Notice there's no temperature change in there, because there is no temperature change during a phase change. So again, Q is heat energy. That's heat energy measured in joules. M is the mass, and then in kilograms. And then L is the latent heat, and it has unit of joule per kilogram. Okay? Now, for example, let's look at water again. Right here. Now, this region is referred to as the latent heat of fusion. That's the term for melting. Latent heat of fusion. And then up here, this is referred to as latent heat of vaporization. Okay? So for water, the latent heat of fusion, which you'll see it as L sub F for fusion, the latent heat of fusion is 334,000 joules per kilogram. Now, what does that tell us? Well, it's pretty simple. What it tells us is if you had right there, if you had 1 kilogram of ice at 0 degrees Celsius, 0 degrees Celsius, so 1 kilogram of ice right there, how much energy is required to get that across to water? 334,000. It's energy per kilogram to make the phase change. Does that make sense? Okay, latent heat of vaporization. So for water, the latent heat of vaporization is 2,260,000 joules per kilogram. And again, guys, don't memorize this. I'm going to give it to you. I just want you to see it. So what is this latent heat of vaporization telling us? If you had 1 kilogram of water at 100 degrees Celsius, so right there, ready to vaporize, how much energy is required to get it across to steam? 2,260,000 joules per kilogram. Yo.
That's all of it?
That's the whole kilogram. The whole kilogram. So what if you had 2 kilograms up here? If you had 2 kilograms at 100, it would just be double that, 4,520,000. Right? What else was I going to say? I had something else I was going to mention. Okay. Oh, I know. Back to specific heat. I forgot to say one thing. Look at, so the specific heat equation, Q equals MC delta T. Just be aware that ice, water, and steam have different specific heats. Each phase has its own specific heat. Okay? All right. Let's go to the next topic. So calorimetry is the next topic, and then we're done. Okay, so calorimetry is the study of heat transfer from one object to another. So here we have hot copper and cool water. A chunk of hot copper and a beaker full of cool water. Let's say that the copper is object 1, the water is object 2. Okay? The hot copper gets dropped into the cool water. What's going to happen? Well, which object is going to lose heat? The hot copper. Which object's going to gain heat? The water. Assuming no heat loss to the surroundings, right? We're going to assume that no heat escapes to the surroundings. Everything stays contained. Nice, you know, in physics we always make those nice assumptions. No heat loss to the surroundings. Heat loss equals heat gain. The heat lost by the copper must equal the heat gained by the water. Is that a pretty easy concept? Okay, so now let's put equations to this. So there's 2 equations for heat. We got Q equals MC delta T, and we got Q equals ML. Now, right here is where I decided that I was going to move the quiz, because you know I said quiz Friday. Right here during period 0, I was like, oh yeah, this is going to need some more time. So, okay, everybody move the quiz. Right here. Now, in this situation, let's just say there's no phase change, right? let's just say the hot copper goes into the cool water, the copper cools, the water warms, no phase change. So which equation would we be working with if there's no phase change? The first one. This is the one, right? So we go like this. The heat loss equals heat gain. Negative Q1 equals positive Q2. So the negative just indicates what? Heat loss, right? The copper loses heat, the water gains heat. So then this is the equation that applies. So you go negative M1 C1 delta T1 equals M2 C2 delta T2. And then you solve for whatever you're looking for. Now look, this negative right here, that negative is going to cancel because what else is negative? The delta T1, because the temperature of the copper goes down. So the negatives are going to cancel, okay? My advice to you when you're doing these problems, absolute value the heats. Just say absolute value of heat loss equals absolute value of heat gain, and you'll be good. Now, there's one exception to that. If the problem asks you to find the equilibrium temperature, you have to leave it non-absolute valued. You have to leave it like that if they're asking for the final temperature. And you'll see why. We're going to solve some problems later in the week. But for now, I want to just introduce a calorimetry problem, and we're going to start class tomorrow with this. So here we have the hot chunk of copper. So I give you the data. The hot chunk of copper gets dropped into the cool water, and you're solving for what the mass of the water must be. Okay? We're done. So tomorrow we'll pick up with this. So copy this into your notes, because I'm going to turn the projector off because I got to finish working on your midterm review. So copy this down, and we'll start class tomorrow. You got the answer here, and that's it.